Welcome everyone to our video on collision theory and the factors which affect the rate of reaction. In this video, we are going to describe how collision theory explains the rates of reaction. We're going to look at the factors which impact the rate of reaction, and we will use collision theory to explain what's going on at the molecular level when we affect the rate of reaction. We know from previous chemistry courses that chemical reactions involve the rearrangement of atoms to form new species, and that is done through the breaking and forming of new chemical bonds. Collision theory states that in order for a reaction to proceed, molecules must collide with each other. For a factor to impact the rate of reaction, it must impact either one of the two postulates of collision theory. Our first postulate states that the rate of reaction will change if the number of collisions per unit time changes. So what are we looking at here? Remember, a rate is always a change over time. So we can change the total number of collisions by just letting a reaction proceed for a very long time. A rate of reaction is changing if we are changing the collisions in a given amount of time. The number of collisions per second, the number of collisions per minute, the number of collisions per hour, the number of collisions per any unit time. Our second postulate is going to have to do with energy in collisions, because it turns out that not all collisions are equal. For a collision to occur successfully, the particles involved must have sufficient energy to overcome those repulsive forces that start to increase drastically as they approach each other. So as two molecules approach, suddenly you have all the repulsive forces from the electron clouds, and as they get even closer, you have the huge repulsive forces from the positively charged nucleus. Those particles have to be moving fast enough. They must have enough kinetic energy to overcome those repulsive forces. In many situations, the orientation of the particles matters as well. This may not apply to simple molecules such as ions or point particles, but as we get larger and more complex particles and molecules involved, the orientation also matters in terms of having a successful collision. So postulate 2 states that the rate of reaction will change if there's a change in the percentage of successful collisions. Let's now look at the different factors which impact the rate of reaction. Many of you will already be familiar with the fact that increasing the temperature increases the rate of reaction. Well, temperature is just the measure of the average kinetic energy of the system, or it's really the measure of how fast the molecules are moving. So if we change how fast the molecules are moving, which temperature measures, that is going to impact both postulates of collision theory. On one hand, as we increase the temperature, there is going to be simply more collisions per unit time because the particles are moving faster. They're just going to be encountering each other more often because of their increased speed. Now let's consider how temperature impacts the percentage of successful collisions. It's useful in this case to observe a Maxwell-Boltzmann distribution. If you're not familiar with this distribution before, the y-axis shows us the number of molecules in a given sample. The x-axis shows us increasing kinetic energy. The way to interpret this distribution is that the higher the curve, the greater the number of particles at that particular energy. So in this case here, if I observe the highest point on this curve, that's telling me that there's the greatest number of particles with that amount of kinetic energy at that particular temperature. So we know there's a distribution here because in a given sample, there's going to be some particles with high kinetic energy, there's going to be some particles with low kinetic energy, but a vast majority of the particles fall into some sort of middle range. For a given chemical reaction, there's going to be a minimum amount of energy required for a successful collision, and for that amount of energy is referred to as the activation energy, which is shown right here. Only molecules which have at least that activation energy will undergo successful collisions. So all of those molecules which have energies to the left of the activation energy on this distribution will never undergo successful collisions. When we change the temperature, that shifts the distribution so that there's going to be a different percentage of molecules which have the activation energy. Consider the diagram on the right. In this case, temperature 2 is a higher temperature than temperature 1. So you can see here that the curve has shifted to the right. As a result, the area under curve 2 at T2 is greater than the area under T1 above the activation energy line. So there's going to be more particles at temperature 2 with the activation energy. The next factor that we will consider is changing the concentration. Remember that we can change the concentration of any impure substance in solution, and we can also change the concentration of a gas because a gas can be compressed and will always take on the volume of the container. Because as you increase the concentration, there's going to be more particles in a given volume. As a result, with more particles, there's going to be an increased likelihood of collisions, so more collisions in a given unit time. Many of you are familiar with the term catalyst from either previous chemistry courses or from biology courses when you talk about enzyme. A catalyst is any chemical which is used in a chemical reaction but is not being consumed. In the context of reaction rates, a catalyst provides that reaction or the reactants with an alternative reaction pathway which has a lower activation energy. Since catalysts impact the activation energy, that is going to change the percentage of successful collisions. We can illustrate the impact of a catalyzed reaction looking at a potential energy diagram. Recall that the difference in energy between the reactants and the products is our difference in enthalpy right there. So here we have an exothermic reaction where the reactants have a higher internal energy than the products. In this potential energy diagram, we've shown a curve which illustrates the activation energy. In this case, the reaction does not occur spontaneously. We have to put in some energy to get the reaction going, and that is the activation energy here in the red line. A physical analogy is helpful here. Imagine we want it to roll a ball down a hill, but in order to get the ball rolling, we first have to roll it up the hill. So we have to put in some energy here. But once we reach the top of the hill, the ball is going to roll down the hill all on its own. It's similar to what's happening here. In order to get the reaction started, we have to put in that activation energy. But then once it's started, it's going to proceed on its own. When we add a catalyst, we decreased the height of that hill. So we have to put in a lot less energy in the catalyzed reaction. We often think of catalysts as increasing the rate of reaction, but we can also have negative catalysts. We use the term inhibitor as any negative catalyst which slows down the rate of reaction. An inhibitor slows down the rate of reaction by increasing the activation energy by providing an alternate pathway. A poison is a specific type of negative catalyst which totally blocks the reaction pathway and thus stops the reaction. Our next factor is that of surface area. Surface area is a factor which largely impacts any sort of chemical in the solid state. By changing the surface area of a solid, it impacts the amount of particles which are available to collide, because when we have any reaction that involves a solid, the collisions can only occur on the surface of the solid. So, if we are increasing the amount of surface available, we are going to have more collisions per unit time. The final factor which impacts the rate of reaction is something we refer to as the chemical nature of the reactants. This factor can impact the number of collisions per unit time or the percentage of successful collisions, and it depends on the situation. When we're talking about the chemical nature, we're talking about having the same type of reaction, so say a reaction that involves an acid, but we change the specific acid involved, because by changing the specific acid involved, that will increase or decrease the rate. A good example would be comparing a strong versus a weak acid. A strong acid, which ionizes completely, is going to often cause a reaction to occur more quickly than a weak acid. Another example would be a reaction that involves a metal losing an electron or electrons. That reaction would be impacted by the activity level of that metal. So metals that are high on the activity series, such as lithium, sodium, potassium, would cause the reaction to proceed more quickly than metals which are low on the activity series, such as gold, silver, and platinum. Another example would be changing the chemical so that fewer bonds must be broken for the reaction to proceed. In all these cases, we have to remember that we're keeping the reaction the same. We're just often changing the chemical identity of one of the reactants to cause a change in how the reaction might proceed, either increasing the percentage of successful collisions or changing the number of collisions per unit time. This concludes our video on collision theory and factors which impact the rate of reaction. What you should be able to do with this is, given information about a chemical reaction, you should be able to identify different ways in which we could impact the rate of reaction and explain at a molecular level, using collision theory, why those different factors are changing the rate of reaction.